There is exactly one company on Earth that can stop the AI boom. Not NVIDIA, not TSMC, not Apple. A single Dutch company in a small town called Veldhoven with about 40,000 employees and a market cap of more than $300 billion. Their name is ASML, and they make the only machines in the world that can pattern modern leading-edge silicon. If ASML ships fewer machines next year, every advanced node TSMC, Samsung, and Intel are planning slips by months. If ASML stops shipping entirely, the entire AI industry runs out of new chips in roughly 18 months. So in the next 13 minutes, I'm going to walk you through why this monopoly exists, what is actually inside one of these machines, why no competitor has emerged, and what the next decade looks like. First, the size of the monopoly. ASML is the only manufacturer of extreme ultraviolet lithography machines, called EUV. EUV is the technology that lets the industry pattern features below 7 nanometers, N5, N3, N2, A16, all of it. Without EUV, you cannot build a modern AI accelerator. There are no second-source suppliers. Nikon and Canon, the two competitors that used to share the lithography market in the deep ultraviolet era, walked away from EUV development 20 years ago when the engineering looked impossible. A current generation EUV machine costs around $170 million. The next generation high-NA machine costs around $380 million. Each one weighs about 180,000 kilograms, heavier than a full Boeing 747. It ships in roughly 40 cargo planes worth of components, takes 9 months to install in a fab, and another 6 to 12 months to qualify. ASML produces 40 to 50 EUV machines per year. Demand is multiples of that. This is the most expensive, most complex, most concentrated monopoly in modern industrial history. And the reason no one can copy it has very little to do with patents. It has everything to do with what is physically inside the machine. Let's open one up. Component number one, the light source. Generating extreme ultraviolet light at 13.5 nanometers is, no exaggeration, the hardest physics problem in modern industry. ASML does it through a US subsidiary called Cymer, based in San Diego, which they acquired in 2013 specifically to bring this capability in-house. Here is how it works. A drop of molten tin, 25 microns wide, about a quarter of the width of a human hair, falls through vacuum at a rate of 50,000 droplets per second. As each droplet falls, a powerful pre-pulse laser hits it and flattens it into a thin disk. Then a few microseconds later, a far more powerful main pulse laser hits that disk and vaporizes it into a plasma at hundreds of thousands of degrees Celsius. That plasma emits a brief flash of EUV light. That flash is what patterns silicon. Read that again. 50,000 tin droplets per second, each one struck twice by separate carbon dioxide lasers with sub-microsecond timing precision in a vacuum chamber. The system has to maintain this for years, 24 hours a day, with maintenance windows measured in hours per quarter. The carbon dioxide laser system that drives this is, by itself, one of the most expensive industrial lasers ever built. Trumpf, a German company, makes the laser. The vacuum chamber, the droplet generator, the alignment optics, all of those are themselves multi-decade engineering challenges. Cymer needed 30 years to make this commercially viable. Anyone trying to build a competing EUV system would be starting that 30-year clock from zero. Component number two, the optics. EUV light has a very inconvenient property. It is absorbed by almost everything, including air, glass, and most known materials. So you cannot use lenses. There is no lens material that is transparent at 13.5 nanometers. Instead, EUV machines use mirrors, and not ordinary mirrors. Multilayer Bragg reflectors, made of around 40 alternating layers of molybdenum and silicon, each just a few atoms thick, deposited with sub-nanometer precision. Even those mirrors only reflect about 70% of the EUV light hitting them. Each EUV machine has 6 of these mirrors in a row. So by the time light bounces from the source to the wafer, you have lost more than 90% of the original power. Every percent of mirror reflectivity matters. Every nanometer of mirror flatness matters. The mirrors have to be polished to an accuracy that, scaled up to the size of Germany, would be measured in tenths of a millimeter of variation across the entire country. These mirrors are not made by ASML. They are made by Carl Zeiss SMT, a German subsidiary of Zeiss, which has been refining its optical manufacturing for over a century. Zeiss makes them in a single facility in Oberkochen, Germany. ASML and Zeiss have a deep, multi-decade joint development agreement, and ASML even owns a stake in Zeiss SMT. The optical chain, like the light source, took roughly 30 years to bring to volume. There is no second supplier. So now you have a Dutch machine company with a US light source business, a German optics partner, and a vacuum chamber held together by hundreds of thousands of precision components. That is just the body of the machine. We have not yet talked about what it patterns onto. Component number 3, the photomask, which the industry calls a reticle. Each chip layer is patterned by projecting EUV light through a reticle onto the wafer. The reticle is essentially a stencil. For EUV, that stencil is itself another reflective multilayer mirror with the chip pattern etched into an absorbing layer on top. EUV reticles cost around $300,000 each. A leading-edge chip uses 60 to 80 distinct reticles for all its layers. Reticles are extraordinarily delicate because a single particle of dust as small as 10 nanometers can ruin a wafer or even contaminate the entire production run. To protect the reticle, the industry uses a thin protective film called a pellicle, suspended above the surface, that catches stray particles before they reach the active area. Here is the part that surprises most people. The world has very few suppliers of EUV-grade reticle blanks and pellicles. Hoya and AGC, both Japanese, dominate the blank market. The pellicle, originally a major bottleneck, was eventually solved by ASML in collaboration with Mitsui in Japan. So even the consumables that go into an EUV machine, the masks, the blanks, the pellicles, sit inside another tightly held supply chain that is again concentrated in 2 or 3 countries and a handful of companies. This is why export controls on EUV are so geopolitically explosive. To recreate this stack, a country would not just need to build a machine. They would need to recreate a Dutch lithography company, a US laser business, a German optics specialist, 2 Japanese mask material companies, and the integration know-how that holds them all together. No country has even started that race seriously because the cost would be measured in tens of billions of dollars in decades of time. Now the next chapter, high-NA EUV. Standard EUV scanners have a numerical aperture of about 0.33. Numerical aperture is the optical term that determines, very roughly, the smallest feature you can resolve. Higher NA equals smaller features. High NA EUV bumps the numerical aperture from 0.33 to 0.55. That sounds like a small change. It is not. To physically achieve a higher NA, ASML had to redesign the entire optical chain. Bigger mirrors, a different mirror geometry, a smaller exposure field, and a substantial change to how the wafer stage and reticle stage move during exposure. The high NA system is, in many ways, an entirely new machine. Intel was the first commercial customer. They bought the first production high NA tool, a system called the XE5000, in 2024, and have been ramping it for the 18A process node and beyond. TSMC and Samsung committed later, with Samsung notably hesitating on cost. Intel's bet on high NA, alongside their own backside power delivery technology, is the most optimistic part of their roadmap. If it pays off, they have a window to compete with TSMC at the leading edge. The price tag, again, is around $380 million per high NA tool, plus another roughly $100 million in install and qualification work. ASML can produce only a small number per year through 2027, perhaps 10 to 20. Demand is multiples of that. So even within ASML's own monopoly, there is a tighter monopoly on the next generation high NA capacity, and Intel, TSMC, Samsung, and the hyperscalers are all in line for it. So what is the verdict, and what would actually break ASML's monopoly? ASML wins through 2030, probably beyond. The reason is simple. The gap is structural, not legal. Even if every patent expired tomorrow, no company on Earth could replicate the tin droplet system, the multilayer mirrors, the reticle ecosystem, the alignment systems, and the integration know-how in less than 15 years. The combined capital investment to recreate the stack is somewhere in the high tens of billions of dollars. And the customer base, TSMC, Samsung, Intel, Micron, SK Hynix, has zero appetite to qualify a second source even if one existed, because qualification of a new lithography supplier takes years of risk that no foundry will absorb voluntarily. There are three things that could partially break this monopoly, and you should watch all of them. First, geopolitics. The US has pressured the Netherlands to block EUV exports to China. China has spent the past decade trying to build domestic alternatives with companies like SME working on advanced deep ultraviolet systems. So far, the gap is enormous, and SME is realistically a generation or two behind, even on DUV, never mind EUV. But China will keep investing because the strategic stakes are too high not to. Second, alternative architectures. Some of the major hyperscalers are exploring whether you can route around lithography limits with chiplets, advanced packaging, and 3D stacking. If logic density per chip stops mattering as much because you can stack and integrate, ASML's monopoly becomes less existential. This is the bull case for TSMC's CoWoS-L, for HBM stacks, and for advanced packaging in general. Themes I've covered in earlier videos in this series. Third, ASML itself. The company has explicitly said it will only ramp high-NA capacity gradually, in part because the technology is so hard, in part because they have very little incentive to oversupply a market they already dominate. So the constraint on AI compute through this decade is not really NVIDIA's roadmap or TSMC's nodes. It is how fast ASML decides to ship machines. That is the honest answer. The AI boom does not run on GPUs. It does not run on memory. It does not even run on TSMC. It runs on a small number of Dutch machines that very few people on YouTube have ever discussed seriously. If this was useful, subscribe. This channel is where the actual semiconductor industry view of the AI race lives, not the marketing slides. With this video, the AI supply chain series is complete. GPU versus TPU, the HBM cartel, TSMC's monopoly, and now ASML upstream of all of it. Drop a comment with which direction to take next. Thanks for watching, and I'll see you in the next one.